Yeah, thank you very much. It's a pleasure to be here. It's been fascinating to me, the whole meeting. And I'd like to discuss some of the fMRI neuroscience results we've been doing at MGH, and I want to just highlight that, of course, this was mainly work done by my collaborators, John Palomini, who some of you heard a few days ago, and Christina Triantafilou. So our goal is to try to advance the methodology of fMRI to be able to study large sections of the folded cortex for its radial and horizontal specialization, namely columnar and laminar organization. Anyway, let me illustrate this point by some of the really fascinating and very informative early work done to, say, look at columnar structure. This was a study, amazingly, it was done 10 years ago on a 4T. I think Alan is in the audience. Yeah, there he is. And they really did a smart job of figuring out how the geometries of, in this case, ocular dominance columns would lie in the folded cortex with the slice placed in different orientations. And then they chose an advantageous slice orientation to sort of maximally see the cortical columns. And they were able to do this with a very anisotropic voxel by taking advantage of this sort of unique local geometry and use a 3 millimeter slice thickness. And also at that time it required multi-shot EPI, actually we still would to acquire 0.5 millimeters, well, maybe not. But the thing that we wanted to advance about this, and again it's a beautiful study, but it looks at a very focal area and it doesn't give you a chance to see the architecture over folded regions of cortex. And it also doesn't give you the chance to utilize the layer-specific information in these ocular dominance columns. For instance, that the spatiality is peaked in layer 4C of the cortex. And so, and here's a later study that was shown by the last speaker, by Yakub and his colleagues, where they also took a flattened piece of cortex, and you can kind of see underneath this area how it is sort of folding in and out, so they're sampling different laminar depths. It's actually very hard to find somebody with that flat a calcareous cortex that can be that large of an area can be seen in a single 3 millimeter slice, but they were able to see in this case both the ocular dominance columns and the orientation columns. And the 3 millimeter slice, of course, again precludes studying laminar specificity. It also complicates the avoidance of surface veins, and it precludes looking over large regions of cortex. And here's a map of V1 visual cortex, how the visual field is mapped onto human V1, and it's quite a large bit of cortex in primate brain, and it's very nicely organized. And here's a flattened map from a monkey cytochrome oxidase stain showing the ocular dominance columns in this flattened map over all of V1. And you can see this is the sort of architecture that we would love to ultimately capture. A large region of folded cortex, and it has many features like the blind spot here, how the ocular dominance columns meet the V1, V2 border perpendicularly, how they organize around the molecular crescent, and etc. So that is obviously an ex vivo staining technique, or cytochrome oxidase and then ex vivo flattening. We'd like to see this in vivo in humans. And one of the other things we'd like to see is laminar-specific activation, really study the organization of the cortex in the laminar direction. And to do this, of course, Wald needs to be capable of laminar-specific activation. There needs to be local control of the blood flow in the lamina. And that's a very difficult thing to be able to show. It's one thing to see changes in delta S or changes in contrast across the lamina, but that doesn't mean that you're specifically activating one region of neurons, one lamina of neurons, and you're specifically seeing the blood flow response from those neurons. It could be due to, say, a hemodynamic a blood volume change across the cortex, etc. What you need to really prove that Wald is capable of laminar-specific activation is an experimental paradigm that differentially activates adjacent layers to see distinct responses. And of course, that's a very tall order, and it's very hard to imagine a task-oriented fMRI experiment being able to do this. And I'll show you later on how we approach this using resting state functional connectivity. So our goal is to see large sections of folded cortex. So what technology are we going to use to try to get us there? Of course, the improved contrast to noise and improved spatial localization of higher field strengths. Stronger, faster gradients will be really important. We want to move from the multi-shot, 32-shot fMRI to single shot. That's to improve the physiological fluctuations in the sequence so that each shot is taken in a unique physiological state. And absolutely critical has been highly parallel array detection. I think everyone has been surprised by the quality of 7T EPI, and I think more than anything else, it's the highly parallel array detection and the fact that it works better at higher field than it does at 3T and 1.5T that we really have to thank for that. And so our goal is gradient echo single shot for maximal parenchymal SNR and laminar analysis for draining vein avoidance, and simultaneous multi-slice for efficient whole brain coverage at high resolution, which is, of course, the missing piece of the puzzle that we heard Camille talk about earlier. Now, previously, people have shown differential responses across layers. For instance, that the earliest and greatest bold response is in the central layers. This has been shown in gradient echo bold and spin echo bold, cerebral blood volume using an iron contrast agent, blood flow, and people have seen relative differences between signal sources. Not necessarily indicative that there's little valves in the cortex controlling blood flow in a laminar-specific way. And people have also seen differences in response across the layers in non-MRI, in the barrel cortex through clearance probes, blood flow rate localized to specific layers in laser flow, Doppler flowmetry, and autoradiography. And the most interesting one is that the flow response seems to be regulated to within individual glomeruli within the cortex. So to me, it's very important to see this non-fMRI or non-MRI evidence that blood flow is possibly regulated at the sort of laminar level within the cortex. And finally, two-photon microscopy was used in the last one, sorry. Mechanisms for local flow regulation within the lamina, direct neuronal control of vascular sphincters, capillary regulation of capillary diameters within the cortex by pericytes, upstream signal processing. A lot of things have been postulated, and we don't exactly know what might be important, but at least there's some potential mechanisms. So looking at our experiments, we're using the Siemens 7T. I'll show you results mainly from the AC84 head gradient set, but also some more recent images from our SC72 body gradients, which we switched to about 9 months ago. 32-channel phased array receive coil. I'll show a little bit from that. Also, our MRI acquisition is always an isotropic resolution. We really want to see in the folded cortex, we need isotropic resolution, single shot to reduce the physiological fluctuations. And our standard acquisition is a 0.75 millimeter isotropic single shot bold. Here's some parameters, heavily partial Fourier, heavily use of grappa. With the head gradients, we can get away with only a grappa of 3 to reduce the echo spacing down to something reasonable, and the EPI readout train to something reasonable. With the body gradients, we use a slightly longer effective echo spacing. We can actually go lower without the stimulation monitor tripping, but we get some ghosting, and so if we could fix that, we could bring this down so that the final effective echo spacing was actually pretty similar to the head gradients at a cost of one more step up in the grappa factor. But of course, it's important to have that large bore for visual stimuli and also to allow us to do the next step in coil development. And I simply have to show a coil to talk about this because I think it's absolutely critical to our studies that we have the best coil that we can imagine. And this was a second generation of Graham-Wiggins 32-channel coil that was made by Boris Keel, where he really took the time to make it much more robust. It's still a fairly difficult coil for the patient to slide into. Almost everybody fits in it, but it's still a little, you have to kind of worm into it. And our next generation, we're working on that with a splittable design like we're building at 3T now. And we've seen some of the fMRI. Here's a 1 millimeter single shot. And again, when I started this in 2000, got our first EPI in 2001 on the 7T, we were really not at this level. And it was really, I think, an open question of whether single shot EPI was going to be viable at 7T. And now I think it's a testament to the 7T community that now everybody takes it for granted. This is absolutely routine. And in fact, it's amazing to me that the single shot imaging is actually higher resolution than our anatomicals. So why are we making surfaces based on 1 millimeter MP ranges when we have these beautiful 1 millimeter echoplanar images that do have some distortion, but if we make the surfaces based on those, at least we'll have matched distortion. And you can really see that there is some blurring during the EPI readout. It's not instantaneous, it's longer than T2 star, but I think you can appreciate that these are not hugely blurred images. Here's some going down a little bit lower. Now this was taken with our SC72, so we moved up to a Grappa factor of 4, of course coronal plane. I'm showing you also the average of 10 shots, so of course an individual shot is roughly 3 times noisier than these. But I find that it helps you appreciate any potential blurring in the image to take these averages. So I'm not trying to pull the wool over your eyes on the noise in the image. I'm just trying to better appreciate the cortex. And here's a zoom in on those 0.9 millimeter 7T EPI with the SC72s. And here's some 0.5 also taken. Actually, I'm not sure which gradients these were taken. Oh, it must have been the head gradients because it's Grappa 3. Here's Grappa 4, so that's the SC72 gradients. And zooming in, you can see it's quite good at 0.75. Again, a little more distortion with the body gradients, even though we've upped the Grappa one step. So we need to get to work and build a better coil. We can push this even farther. These are 0.5 millimeter isotropic single shot images. Again, the average of 10 shots. And as you can see, they're getting noisy. But remember, in an fMRI time course, you'll have hundreds of these images, and you'll be looking for activation in a sort of average over hundreds of these. We still have a limited field of view, and we're only covering the top of the head here. So I want to take a step back and look at some ex vivo images, because this has been very helpful to help us cut our teeth for the laminar surface identification and to help predict Brodmann areas in vivo. And to do this, again, the coils were necessary. This is what happens if you stick a hemisphere in a 3T coil. I think it's a 6-hour image, just stuck in the 3T head coil. Take a proton density image. Here's the 32-channel coil with a matched acquisition in the 7T scanner, and you can really appreciate that building a specialized coil for your ex vivo hemisphere gets you a long ways. There's a coil up in the corner. And here's some just different cross sections through that volume. It's an isotropic 150 micron volume. And we're able to push it down to around 100 microns, which is sort of a holy grail for the whole hemisphere, because it really then allows us to interrogate the lamina. And this is actually very hard to get to in a whole hemisphere. There's plenty of examples where somebody's taken a little finger-sized chunk of cortex and gotten to 50, 60 microns isotropic. But doing it over a whole hemisphere is a very different thing. And here's the sort of thing we want to do with it. This is work by Bruce Fischel, where he automatically found the gray matter surface, but more importantly, he also automatically found this subsurface between the granular layer and the supragranular layer. And this really allows us then to study, going the wrong way, how the lamina change in position as a function of the local curvature of the cortex. And if you look down here in a gyrus, you'll see that these lower layers are expanded, whereas in a sulcus, they're compressed. So if you just divide up the cortex into equal layers, like I'll show you we do currently, you won't actually be mapping lamina, you'll be mapping different depths in millimeters. And our ultimate goal is to map laminae. So we need to know how this is going on in the brain. And the way we do it is with that ex vivo exam. And here's where the distance between the supragranular layer 4 boundary mapped in millimeters, and as you can see, it's very well correlated with the curvature. So this gray-white thing shows the positive and negative regions of curvature, and this color bar scale shows basically the distance to that lamina, and showing how it's compressed in areas of positive curvature and vice versa in areas of negative curvature. And the other thing that was very interesting, just with this ex vivo study, Oliver Hines was able to do some real neuroscience. He was able to, of course, automatically, very accurately see in 3 dimensions where the line of Gennari stops and starts, and then do this in a number of subjects and reconstruct the surface. And then he can do this and see how it varies across individuals. And it was really amazing to me that all humans essentially at least have essentially the same shape for V1 once it's flattened, with the exception of a scale factor. And in fact, if you do it in monkey brains, you also get the same shape relative up to a scale factor. You know, Van was talking about comparing us to possums. I'm not quite sure about those, but at least between primates and us, it's pretty similar. And even more impressive than the consistency across subjects is that these things really follow the cortical folds. So using the ex vivo data, half of them as a training set and half of them as a validation set, we can, Bruce Fischel and Oliver Hines figured out that they could figure out where V1 is amazingly precisely just by looking at the folding pattern in the cortex. And we use that now all the time to define V1 ROIs. So you train on ex vivo brains, and in this case we're predicting it in vivo and then validating the prediction with retinotopy. And of course we can't quite get all of V1 because we can't excite the periphery. So the other key feature was being able to align these single-shot high-resolution images to the cortical surfaces. As you can imagine, if the surfaces are made from an MP range with very low distortion, this is a problem. And to do this, Doug Grieve developed a method where the gradients in the cortex of the EPI actually drive a rigid or non-rigid alignment to the MP range. And this has been very helpful because it really uses the information in the echoplanar image to drive the alignment, and not the skull or the chin or God knows where outside the brain, but really the anatomy that you're interested in, the cortical layers, which, as you saw in those EPI, you can see just fine where the cortex is. And it has a very high accuracy, which we can go through and check by just superimposing the surfaces on our EPI. And this is critical to us because if we want to do laminar-specific, we need to make sure the surfaces are accurate. Then we can draw subsurfaces, as you heard before. In this case, they're equidepth in millimeter subsurfaces, so they're not corrected for the curvature. And then we can analyze our fMRI voxels and say, just give me the voxels that are touching surface number 5 in this set, or surface number 3 in this set. And that was work done by John Palamini. And part of our goal for this was to expand our definition of the biological point spread function. We often hear, oh, it's about 2.5, 3 millimeters at 7T, but is this really the end of the story? And we like to split it up into 2 possible PSFs, a horizontal to the surface and a radial PSF. Are those really the same? Well, maybe, maybe not. And we also suggest that it's very unlikely to be similar radially because of the very heterogeneous vascular anatomy, specifically these Peel vein sublayers, which has the big draining veins which cause so much angst in fMRI, compared to just diving vessels and, of course, the capillary bed. So we chose to test this in a retinotopy task where we utilized this well-known mapping of the visual field onto the cortical surface, which is a logarithmic mapping. It was first done in 1982 in a monkey with radio tracers, and now at 7T we can easily get pretty good retinotopy in a 10-minute exam. This is some work from John Palomini at 2 millimeters isotropic, so this is what we call a low-resolution exam. And then we wanted a test pattern that we could put up on the cortex, and we chose an M, and then we pre-warped it to this logarithmic mapping so that when it's undone onto the flattened cortex, as if you would take out the monkey brain and flatten it onto the film, then you would see an unwarped M. And so here's the actual stimulus. You can see it kind of looks more like a W, I guess, but flashing, in one condition, flashing inside the M, other condition, flashing outside. We simply do a standard fixation task to make sure people are really fixating, and a block design 5-minute run. And here's the result. Not very illuminating, and this really underscores why we don't look at our results on slices. You can't see anything about the architecture of the cortex. You see a little bit more when you show it onto the folded surface of the cortex, and now you can just appreciate the M kind of tucked into the folds. But it's really when you inflate it that you see that everything's working. And so there it is on the unfolded cortex. And this, I'd like to emphasize, this is a 5-minute design, and a lot of stuff went into this, from making sure the fixation is okay to making sure the surface is aligned. Everything has to kind of hold together. So it was sort of our test set for what we hope to be a variety of sort of resolution measurements. And I like to present it this way. This is unsmoothed, unthresholded activation. So no burying anything under a threshold. And then we went on to do the laminar analysis, where we looked at just the voxels at different depths. And of course, we don't have 10 voxels across the cortex, but we can still divide it up this way because we have a lot of voxels. And we see that near the peel surface, indeed, we get kind of this blobby M, which is likely due to the peel veins contaminating the fMRI in those voxels. But as you move away by maybe a third of the cortex, things clean up nicely in the center, getting a little bit weaker as you move to the white matter surface, where presumably we're partial volumed with a good bit of white matter. So that illustrates just our first level approach to improving, in this case I'd call it horizontal point spread function, by moving to deeper cortex. It also illustrates a point that the point spread function is not summarized by one Gaussian number, one zero mean Gaussian number. It really gets blobby in kind of a strange way that, likely affects the ropey veins on the peel surface. So let me speed up a little bit. John was able to, of course, quantify this, and we didn't do it with a zero mean Gaussian, but we did it with a correlation to the stimulus pattern, warped for a slight offset in fixation. And of course, near the white matter, we get a significantly better point spread function than near the peel surface. And it's very interesting to look at the partial voluming of voxels in this acquisition, which I should say is a 1 millimeter isotropic acquisition, that there's barely any voxels that are just cortex. Everything is contaminated a little bit by either white matter or CSF. And another good reason to go to high resolution. As a matter of fact, when you look at the z-scores and kind of distribute them in this funny way, you find that the highest z-scores are from the voxels that have the largest CSF contribution. And that suggests, of course, the peel voxels, contaminated most with the draining veins, but you just have to move a little bit away in point spread function and take a little bit of a hit in Z statistics to get more pure gray matter voxels. And that's an important point, I think, because you don't have to take a big hit in statistics to move one step away from the peel veins. It's important to point out that this was a differential response. We were subtracting two stimulus conditions. Therefore, it allows us to subtract out the common mode activation of this. And as you can see, when you look at the individual conditions, there's a lot of that. So we're relying a lot on this common mode subtraction. So I think our conclusion is you need to avoid the surface vessels to get the highest resolution. But one of our other conclusions was you don't need to avoid the surface vessels. Actually, we got a pretty good M just without avoiding it, and I think in many applications in neuroscience, it'll be just fine. And one of the reasons for doing this study for us is it was sort of a warm-up to get to this fMRI in the flattened cortex, because everything hangs together. We have to have all of these components coming together accurately to really get that M to look like an M. And this is my physicist approach to, multivariate decoding. I can just look at that and say, oh yeah, the subject's seeing an M. Some other examples of things that we're doing on the laminar surfaces. Here's a T2 star map at 7T by John Palomini, showing some well-known T2 star stripes in the sensory and motor cortex. This is Jennifer McNabb's cortical diffusion direction analysis, where she does millimeter and submillimeter DTI and looks at the primary direction and sees very, very clearly and divides it up relative to the cortical coordinate system, tangential and radial diffusion, and sees very prominent features which were first recognized by the Leipzig group in cortical diffusion, and we were just following up on that. But I think that this analysis works really well. She also sees some hint that secondary and Heschel's gyrus have this same tangential pattern. And it allows us to really think about cortical diffusion in order to help define cortical areas by being able to paint directions onto subsurfaces in the cortex, and the laminar analysis is really useful for avoiding partial volume effects. And the next thing we wanted to answer was how low can resting state studies go? And this is work by Christina Triantafilou showing the default mode at 0.75 isotropic, and I believe with zero smoothing, and showing that we can really see these signatures of resting state connectivity at quite low spatial resolutions, or quite high spatial resolutions, I should say, at 7T. And I think this is important. The last speaker said for really validating very local connectivity patterns within regions of cortex. And that's our goal as well. Again, the default mode at 0.75. And here's some coronal 900 micron isotropic seed region in the right motor showing connectivity to specific subregions of the cerebellum. So this is not a local connectivity, but very long range. But being able to, the cerebellum is of course much more difficult and needs higher resolution to really parcellate where different areas connect to in it. Here's some of the first results at 0.5 millimeters isotropic, and here we're starting to suffer a bit from the signal to noise. The highly thermal noise dominated. Basically, I think we need a better coil for this. And we wanted a test case where we could see retinotopically specific connectivity in V1, and we knew that the connections between the two hemispheres is not present in V1, that it doesn't actually exist anatomically, but of course we see lots of cross correlations. And there may be some topological connectivity from adjacent areas, say V2. And the common drive problem is that part of this binocular region gets mapped onto both hemispheres. And so we have a sort of correlated drive from the retina that's going to make both V1s look correlated when in fact there's no real functional connectivity, there's no real anatomical connectivity. And here's just a look at the resolution as you move the seed region around the lower bank in V1, how the functional connectivity changes. And as you can see, this is more reminiscent of the single condition map, which is a little bit disappointing because we're not seeing the super high resolution. But we can at least see that there is a retinotopically organized connectivity within V1 and across hemispheres as seen by resting state. John went on to do a very small subregion of V1. There's a seed marked in green. And to see where that connects to. And what's really interesting here is we're seeing, of course, connectivity to both hemispheres, whereas the seed was in one hemisphere, but we're also seeing the connectivity to V2. So some of the the corresponding retinotopic spot in V2. So some of the connectivity across hemispheres might actually be mediated via V2. And finally, I want to wrap up with trying to exploit the laminar-specific conductivity, the laminar-specific wiring diagram of the cortex to try to see evidence that BOLD has laminar specificity. And we also think it's a promising method to try to determine directionality in cortical networks and see how much feed forward and how much feed backward connectivity is going on. And we can use these stereotypical wiring diagrams. They're quite complicated in the textbooks, but the sort of 1,000-foot view is that superficial layers, and you know, there's in different areas exactly which layers at 2, 3, or 4A, whatever. From our point of view, we don't even have the resolution to talk about that. I'll just say that superficial areas tend to be the output layers where the axons originate, and then the input layers tend to be the middle layers. And of course, if area 2 is sending information to area 1, it's the other way around. Again, the superficial layers are then going toward the medial layers in layer 1. And if you have a common drive, you just have this third area driving the middle layers of both areas. And so these are the three situations we want to try to distinguish in laminar-specific resting state. So we took an MT seed, and we used both a task activation stimuli and a resting state study to determine the seed. And then we simply plotted the correlation coefficient from one lamina level in layer V in V1 to another laminar level in MT. So peel to peel, peel to middle, peel to white matter surface, etc., to make what we call the laminar connectivity matrix here. And what was very interesting to us is that this actually seems to have features, namely a big blob in peel to peel, which it seems like the surface veins are highly correlated, but also this off-diagonal blob, which corresponds to the more superficial layers of V1 talking to the middle layers of MT. And so that would suggest that V1 is the output layers of V1 are more highly connected to the input layers of MT than vice versa. And that's, of course, something we know already because V1 and MT, while there are some feedback fibers, most of the information is going from V1 to MT. So this is exactly the pattern that you would expect from the wiring diagram. And in contrast, if you look at left hemisphere V1 to right hemisphere V1, you don't see this non-diagonal feature. You just see the peel blobs to peel blobs and then folding off in correlation as you go deeper. And we think this provides some evidence that blood flow is indeed regulated at the laminar level. We don't see why there would be a bump. And it gives us the ability to distinguish between these two situations. The common drive from the retina or V2, which is producing the correlations here, and the feedback specific or the feed forward nature of the V1 to MT connection. And with that, I just end with one slide showing what you can do with simultaneous multi-slice. This is a 1 millimeter isotropic exam, 3x simultaneous multi-slice in 3 seconds, something like 120 slices. This is absolutely this multi-slice, we call it simultaneous multi-slice, same thing Camille was talking about. I think it's going to play an absolutely critical role in the sort of whole cortex studies at 1 millimeter and below. Because how can we do resting state with a TR of 10 seconds? You just can't. That won't Nyquist sample the fluctuations. And with that, I'd just like to thank my collaborators, of course, John and Christina, who provided many of the slides. Thank you.